I tell you, we're ready to record. Okay, so this is what we're doing as well. Pick up where we left off. I'm trying to get through the rest, more or less of this first PowerPoint. I doubt that we'll get through all of it. We'll get through most of it. This is when we really talk about balance more than anything else. And it starts where I ended, as I remember me telling you that I actually reviewed this with the other group just to be consistent. So you can see there was quite a few slides that we went through, which means quite a bit of material. So the part you might recall we ended here, and I don't want to spend a lot of time on this comparatively. Okay, I'm not going to ask you the definition of a solution, but to understand what a solution is, our body is filled with water. Okay, and a lot of that is in solution, which means the particles readily dissolve. We call them water soluble. So whether they are, how should I describe them? Whether they are salts, sugars, even different kinds of proteins, many of these are water soluble. A lot of chemicals make up the internal constituency of fluids in our body, whether in the plasma or not. What's interesting about any solution, even bottled water, which has some minerals in it, we can see through it. That's because the particles are so small, they don't deflect the light. So we can see clearly through it. It may not, I mean, depending on, it may have color associated with it. And a lot of times you do the experiment where you drop a blob of ink or something like that in a beaker of water and it all turns blue or whatever color the pigment was, but you're still able to see through it. When you get to micro lab, that's the way you tell if something is sterile. Sterile liquid is clear. We can see through it. Not clear is what I'm talking, but we can see through it, transparent. And you'll do that when you start to grow cultures in test tubes and things like that. They become cloudy or murky. So the interesting thing about them is we can filter out the particles. It didn't make them less particles. It's just that they're not obstructing our vision of it. So we can filter them out. We can extract them. And the beauty of them being dissolved in water is they can move. And that's where the sodiums and the potassiums and the chlorides can all move from one part of the cell, either into the cell or out of the cell, or from one area of the cell to another area of the cell. They're easily transportable in that regard. That's why solutions are important. Interestingly, inside of our cells themselves, even in the cytoplasm, the liquid that's within our cell, understand that's the beauty of membrane-bound organelles. They're little compartments. The inside of a cell is nasty. It's got variations in chemicals, it's variations in acidity and alkalinity. There's a bunch of stuff going on. There's things that are deconstructing and reconstructing, and you'll see animations of all this that are very, very interesting, I think. But nevertheless, we have what goes on in mitochondria or a lysosome or a ribosome. By and large, it's contained in that area and it's protected. That's the idea of membrane-bound organelles that make that's such a unique thing. And so being able to move things in and out is really important. And that's where the idea of solutions. But a lot of times the cell is not all. The cytoplasm is a plasm, which means it's a mixture of solutions and to some extent gels. And these are colloid, and they can change with what's going on in the cell. Even gelatin dissolved in water. Obviously, when it's warmer, we can dissolve it. When it cools off, it begins to solidify. And in fact, what makes it a gel or a colloid is a protein that you did not know. Gelatin, it holds water to it. What holds the water in our bloodstream, okay, are proteins. The most important of these you will learn is called albumin. You learned that in EDT. What happens, it's holding the liquid in our blood vessels, where at the same time our blood pressure is pushing it out. Blood pressure doesn't push it along like liquid going through a straw. It pushes it along, but also against the boundaries to your blood vessel. So it's not just this way, it's going against all. And when they get down to capillaries, they have little openings and fluid pushes out. Why it doesn't empty itself, the proteins are holding it in. You learn about a neat thing called colloid osmotic pressure when you learn about circulation, and particularly when you learn about the kidney. It's kind of how those things work. So, but what happens is we have what they call sol gel. It's the cytoplasm. Areas where it's a solution, areas more gel-like, and there's variations between. So, and it's interesting, your blood to a certain extent is like that. You take a tube of blood out, you can't see through it. It's just not solid. If we get the idea, if you're using the Jello model, well, it's pretty sturdy, but it really is just holding on to the water. Your blood is both a colloid and a suspension. Okay, suspension is just that. You have parts that are effectively have different components, and it looks uniform when it's moving. But if it stops moving, the components settle by weight. So what the blood bank does, when you donate blood or somebody donates blood, we use different parts. We use the plasma for certain things. There's an area right between where the red cells settle down, they're the heaviest. And then your white blood cells and platelets are in a little layer right on top of this that you learn about when we talk about blood. When you transfuse somebody, giving them blood, we rarely give them whole blood. Only if they're in the emergency room, terrible accident, bleeding inside, gunshot, stab wounds, bleeding outside. You've got to put that volume back in, or water won't do it. You've got to put blood back in right away just to get them stable enough that you can operate and fix those things. Most of the transfusions that we do are for people to restore the amount of red cells because that carries oxygen. And so typically they get what are called packed red blood cells or packed cells. And because the blood bank, they use all of this, they siphon off and they just centrifuge, they spin it. If you just left it alone, it will settle out. If you want to do it rapidly, like the blood bank, can't just sit there and wait for all those bags to settle out. They spin them around, centrifugation, a physical method, and separate. So blood has that role. Blood has protein, so it's a colloid. And the one that you don't see here, there's aspects of blood and aspects of different things in tissues that we call emulsions. It's not about, it's more for me to explain it to you than memorize the definition of colloid, suspension. Suspension you should probably know, okay, of all of these. And solution I would be familiar with. But an emulsion is like mayonnaise. An emulsion is like creamy salad dressing. I mean, you open the mayonnaise jar, it stays there. It doesn't separate out unless it's really bad. Salad dressing, the same thing, creamy salad dressing. If you have that Viva stuff, the Italian salad dressing, it separates out. You have to shake it. You resuspend it. What happens, they have an agent in there that is what we call a bipolar agent. It's positively charged. It's water soluble on one end, fat soluble on another end. You use egg yolks in mayonnaise. If you're using vegan mayonnaise, they typically use mustard, dry mustard and wet mustard in cooking. That's the way you make those things because they contain a magical chemical, don't write down the name, called lecithin, Lecithin. And down the road, you may hear about that depending on where your studies take you. That's why we use those. That's why knowing how to cook is good. Professional chefs don't buy jarred mayonnaise, they make it themselves. Okay. It's one of the, in French cooking, it's one of the mother sauces. You will learn. So solutions, okay, homogeneous in the sense that they're distributed evenly. Sometimes they're heterogeneous in the sense that they have different particles. So, I mean, if you get a mineral water, you have different minerals. They're not all sodium. So there's homogeneous means more uniform in that and evenly distributed, but it implies to some, so I think it's a bad term. I don't use it. These are two terms you got to know. When I ask you a question about this, we talk about movement across membranes, diffusion, osmosis. I'm not asking you is water moving or is sodium moving. I'm going to ask you about solutes and solvents. Solvent is water. That's the universal solvent of living systems. Solute can be the stuff that's dissolved in the water. It could be salt, it could be sodium, it could be potassium, it could be iodine, chloride, glucose. And we look at the relationship between those. It's a ratio between solutes and solvents. It's very important. We'll look at that probably early on when we get to the chapter after this, which starts talking about how things work in the cell. Okay? Very simple. So remember the term solvent. For our purposes, that means water. Water is so important. You're going to see that today when we get to something called hydrogen bonds. Why? Air is a solution. If you didn't know, air is a mixture of nitrogen, oxygen, and other gases, some trace materials, some water vapors. They're all in there. It's 80% nitrogen, 20%. We're at 80-20. That's roughly what R is. Not exactly, but very close to that. And so that's all it is. And everything else is like that. And so this is a big deal. And that's to understand, we don't, thank goodness, you might have heard these terms before. You don't have to know. Molarity. Molality. Don't be friendly. That's chemistry. We don't do that. We do percents. Aren't you happy? So, this is one of the most famous numbers when we talk about things that are called tonicity. 0.0. Percent. Okay? Sodium chloride. You write it like that, it means this is 0.09 grams, okay, of salt in 100 milliliters of water. In biology and life science, we talk about percents. When you get a list of somebody's, we all have them done. If you have a list of their hemoglobin, their glucose, it's all in percents. It means 100 milliliters of whatever it's in, whether it's water or blood or something like that. So what that is normalcy. Makes it normal is the number of particles solute to solid. We're not going to do that. When you show, which is the old story, just like you learned in first grade. It's what it's made out of, and you have to know your units. So sometimes it's going to be in this case it's grams. If you have somebody's blood sugar, let's say they're diabetic, have a good day, they're 85, that's milligrams percent. That means 85 milligrams of glucose in 100 milliliters of water. So that, and you have to, and eventually you're going to have to know what those are. They're not created equal. When you talk about somebody's hemoglobin, which is a measure of their anemia, the normals range from, let's say, 13 to about 17 or 18. That's grams percent. So they're not all created. You know, that's something those are tricky points that people would test you in clinical courses. We will not have that type of stuff. We'll be very generic. It'd be obvious it was something that was, out of bounds. So underlung, that means milligrams or grams per deciliter. Okay. So 100 milliliters would be that. That's actually a typographical error, because it should be 1/10 of a liter is a deciliter. Interesting. Okay. So I'm glad I saw that. But just remember the 100 milliliters of whatever, in our case, water, blood, whatever it is. I'm not going to have to do that. And you're not going to have to remember this. If I give that to you, you don't have to remember Avogadro's number. You're going to see how important it is. That means in a mole of a substance, of a compound, water. Okay, a mole of water weighs 18 grams. That's like half an ounce, maybe a skosh more than half an ounce. In a little half an ounce of water, there are 6, with 23 zeros after it, molecules of water. I don't know what you're thinking. I can't even conceive of how many little, it shows you how tiny the particles are. So you're going to see that water has a certain amount of charge. And that begins to explain to you this concept that we're going to get to, not today, but Monday, pH. Whether something becomes an acid or something becomes a base or is alkaline. It's extraordinarily important. And it all has to do with water. Okay? And a lot of it has to do with this number, Avogadro's number. I mean, chemists do it all the time when you're figuring out, percentages and amounts, and even figuring out the, things that are normal saline and stuff like that. It all plays a role. Okay, so here, colloids and emulsions are not interchangeable. Okay, colloid over time, because of the protein, may change. Emulsions have a longer lifespan, and emulsions typically have to have some agent that will hold that in place. I was talking about that last Again, I'm not going to ask you about that. Okay. And so the idea of sol gel, okay, is that Jello, okay, depending on the temperature, it'll be liquid or gelatin. Okay. Cytosol, well, I used to use the term cytoplasm. Okay, it was, again, this is a sol gel. When we get into the cell, you'll see that that is more significant. It's very much definitional, and I don't think I ask you questions about those. When I do the study guide, and I end up recording a study guide and sending it to you, the way I do it, I tell everybody the same thing. I sit there and look at the test and go, okay, this is blah, 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 blah. You have a written one as well. But I'll be like talking. I remember to do this. And, oh, I pay special attention to that. There's a reason. Trying to help. Again, do not do the night before thing. You will. The second word is up. No, you can't make me. She's going, just say it. Suspensions, okay, settle out, water. Who would make water and sand? It's you're building stuff at the beach. Makes you nothing here is significant. This is everything today. Chemical bonds, sharing of electrons. Everything is predicated on us being able to extract energy from electrons. It's not a physical union. It's a sharing of resources and indeed energy that creates a degree of stability. And we are able to break that bond and effectively extract the energy that is leading to that stability. So the energy relationship is a very useful term to understand. It's not something that's mechanical and strong. And so all of this, and we're going to look at the three major types, and the one that is as important as any of them, which is the weakest. So we're going to look at ionic bonds, two types of covalent, polar and nonpolar, and lastly, hydrogen bonds, which is what makes water special. I'm not going to do this again. Here are our tables up there. Hydrogen, helium, that outermost orbital is 2. Again, all the properties have to do with electrons that are unpaired in that outermost orbital. We call that the valence, V-A-L-E-N-C-E orbital. And indeed, the valence number, it's not identical. It can be identical for ones that are totally different. It's the number of electrons that either have to be gained or lost to create either an empty or a filled shell. Sodium, that column of lithium, sodium, potassium, has 1 electron out of 8, because other than those first 2, hydrogen and helium, the octet rule applies. They all have 8. And because of that, it loses that electron super fast. 1 electron, valence is 1. On the other side, as you look at it on the right, in that sort of light blue, lightest blue color, you have what are called halogens. They're toxins. Fluorine, chlorine, bromine, and iodine. We avoid having those things if possible, and particularly in organic compounds. Okay. They all have 7 of 8. That's what puts them in that column. They're looking to gain an electron in the worst possible way. Their valence is 1. Sodium, potassium, lose 1. Fluoride, chloride, iodine, gain 1. Okay. So they have the same valence number, but in a totally different way that they accomplish it. One loses, one gains. So, and that's the whole idea of that. We're not going to be chemistry classy, I promise you. It may sound like it. You're not going to have to draw diagrams with little dots. You don't have to thank me. You know what they're called? My name, Lewis diagrams. Spelled with my name, L-A-W-I-S. What a country. Love that. So the valence shell, valence orbital, and farthest from the nucleus, chemical reaction, desire aid is the driving force. Yeah. So that's the whole idea of chemical properties. And this is where they finally get to the separation. Helium, neon, the so-called Nobel or inert elements and inert gases, even though it's not all it means, and if you remember that sort of cloud diagram previously, the electrons and an equal distribution of electrons is very important. When we get to that guy over there called methane, the first true organic compound. 1 carbon and 4 hydrogens. All the students who are taking organic chemistry, and typically those are bio and pre, and students in health science sometimes as well. Basically, they're learning about that right now. It's the nomenclature, the naming of these things. Carbon, central carbon with 4 hydrogens, CH4, methane, natural gas. That's really the first of the 2 organic compounds, because we look at covalently bonded carbon to carbon and carbon to hydrogen. I put C.O, that's carbon monoxide. The one that's easier is carbon dioxide, like that, CO2. That is inorganic, even though it's got carbon. It doesn't have any hydrogen, it doesn't have enough carbon. And that fools a lot of people, because the old definition was contains carbon. That's not the case. We understand that. All it means is those electrons are floating around equally, so there's effectively, they don't have to play with anything else. They're happy the way they are. They have physical properties that we addressed, the whole helium and glowing and that stuff before. Well, see it, bye. Moving on. Hydrogen, it's got 1. Remember we addressed that before. Either it's got to lose 1. It really doesn't gain 1 as much as it shares. Hydrogen's big on that. Voila, carbon and 4 hydrogens. 1 electron, so what you have effectively here, messed up drawings. Carbon with a single bond sharing an electron for the hydrogen electron and 1 of carbon's 4 electrons. That's the beauty of carbon. Don't think 2-dimensionally. The fact that we all look at it 2-dimensionally, those hydrogens and those electrons aren't all in a single plane. They could be forwards, they could be backwards, upside down, any angle you want. Think 3-dimensionally. Everything about molecules has a lot to do with shape. Particularly get to proteins. Proteins have unique shapes that give them their functionality. When we lose their functionality, they change their shape. They have a fancy word for it called denature. Changes their nature. Indeed, their shape changes their ability. It's like taking an egg and cooking it. It ain't an egg anymore. It's not liquid on the inside, right? My eggs. Can you uncook an egg? I don't think so. It's like I like my steak a little more rare. You had it for you. Sorry. So the beauty of that, because of the 3-dimensionality, those electrons are being shared here, 2 dots here, 2 dots here, 2 dots here, rather than the lines, are being shared equally at any one time in space. So if that's not a flat molecule, it's round like a little ball. Surely in high school you played with those Tinker Toy things. Yeah. You had the little sticks. And you could twist them any way you wanted to. When you made a double bond, like oxygen, the way it is in nature, you draw it here, stupidly, like that. It has a pair here and a pair here. And the way they form, they are most likely the unpaired electrons are typically closer together than are opposite. Okay. So inherently, there's an asymmetry to that. It's sort of irregularity shape. But what happens when an oxygen makes oxygen, when it pairs up with another oxygen, it kind of does this. The 2 up top and the 2 sort of form pairs of electrons in, like so. So they become, if you look at 3 sets of 2 electrons, go with it. You don't have to know it. I'm just trying to give you an idea. And you form the so-called double bond here. If you remember back in high school, they had like little springs. That meant you couldn't twist the carbon all the way around. That took away a degree of freedom. That starts to contribute to the shape. You couldn't twist it in any direction you wanted to. So that's where the spatiality of it. And we get more and more of that. It's really very interesting. That's why I enjoy it. This is the part this part of teaching is the most fun because you're getting the basics. Basics are the foundation. I know it's cliche-ish. Your sodium, it can't wait to get rid of that. So look what happens. So ions gained or lost in electrons. So it means it's gained or lost when we call it an ion. If it's a positive charge or negative charge. That transfer thing, forget it. Again, sodium in nature is found in its ionic form. Chloride, chlorine with a minus charge, is found in its ionic form. Again, explosive metal, poison gas didn't magically come together and say, I'd love to have your electron. Oh, please take it. Never happened. Okay? They just form together based on a magnetic attraction because there's an abundance of them. There's a whole lot of sodium ions and there's a whole lot of chloride ions. They come together and they form a, quote, salt. Salts are where our ionic bonds, when you have enough of them, that they have a physical presence that you can visibly identify either without or with a microscope. So if it's a negative charge, an ion, just go with it, a negative ion. If you remember that, the opposite, whatever the opposite, if it's cation, okay, it's positive charge. See? So if you only remember one, I always learned a negative ion. I'm sure there's a more sophisticated definition, but I like to, you hear me use the expression like KISS. Keep it simple, stupid. It works. So here they are transferring the electron. See, every freaking A&P textbook does that. Are you blanking kidding me? My eldest and I we were discussing that. We text during football games. Like the guy, that idiot who spat on, if you didn't see it, because we were both had the Eagles in our pool. Sodium and chloride. So now you see the difference. It's gained an electron, so it's a magnetic attraction. Salt is like that. All it is a series of those. And typically salt that you might get, typical table salt, is a mixture. It's mostly sodium chloride, has potassium iodide, it has other quote-unquote salts. What makes salt so unique, why it can form a solution, is water, as you will see, has an irregularity in charge. And water, remember that little amount we have, like a thimbleful of water with all those gazillion, those molecules are tiny, so they, if you're sodium and you're chloride, water can and separate you. Stay on your side. It ionizes, okay? And it separates the salt. If I take away the water, you join up because you're sodium, you're positive. So next time you can be positive and they can be negative. That's a switch. Bad joke. Sure. You have my wife, when she tells me about these stupid jokes, she hates them. Nevertheless, that's what works. So here's the neat thing about salts. If we separate them out, the bulk of what would happen in regular just sodium chloride, it looks like this. There's a whole science in chemistry called crystallography. It is the basis of how we began to analyze DNA. The Watson and Crick model, Watson and Crick didn't figure this out. A lady who didn't get credit until after she died, named Rosalind Franklin. The ongoing story of women in science and in medicine not getting recognition, particularly years ago, it's changing, not fast. My opinion, again, she discovered that with crystallography. We'll get to the story. We can talk about DNA and RNA if you haven't heard it. It's worth repeating. They form nice little squares. They're innocent. Not all crystals do that. Most of you heard of a disease called the gout. Gout is another crystal. It's called sodium urate. Okay. We have a certain amount in our bloodstream that will dissolve. When too much is in your bloodstream, those crystals are like little daggers. Imagine like a sharp knife, big. Okay. And what happens, they settle in joints, they irritate the joints. They're so big that when white blood cells come along to try to get rid of them, the white blood cells can't do it. They explode. They release more chemicals. It's a vicious cycle. And the joint blows up like a balloon, and it's super red hot. You swear it has a monster infection. It's the gout. If you did not know it, if it's untreated for many years, it can kill. It's nothing new under the sun. They saw examples of gout. It's not a modern disease, and hieroglyphics on it in ancient Egypt. Just a little bit. So here's the idea of the sharing. These are equally shared. This is the distinction we must get to between polar and non-polar covalent bonds. When you're looking at equal sharing, why? Because the electrons are equally distributed. Okay? They're all covalent bonds. So here you have the one that I drew up there, and here's a better drawing than I could ever do. This is the resulting molecule. Again, three-dimensionally, an equal distribution of charge, even though you have a positive 6 charge of carbon and positive 1 charges on all the hydrogens, because they're equally distributed at any one time around the carbon nucleus. None of them are pulled closer or pushed farther away. They're all equally distributed. But water, big difference. I told you, this is why I have this up. I told you, water usually is like this. Water has 2 electrons, typically are pulled to one side or the other. And what happens when they meet up with a hydrogen, that way. This is +8. Here on the table, these are still +1, but since they're not evenly distributed, okay, that +8 pulls the electrons closer to the nucleus. What that happens is it creates an unequal distribution of charge. So now here's that water molecule. I know it's hard to see. I'll draw it again. I am this. Did I hear? No, you're not. Hydrogen, hydrogen. It pulls those closer because it's got a charge that is considerably greater than the hydrogen, and it's unbalanced. So the oxygen, by pulling those electrons closer, like a tug of war, tugging them closer, it makes this stuff, the oxygen part, a little more negative. We use this term as the script version of delta, that's like capital letters, small. That, and because it's a molecule and it has shape, it means the area where the hydrogens are is a little bit more positive because it's more stable. That's, so what we have here is a non-polar covalent bond, equal sharing. More of these, the more soluble in fats or lipids, which means it can easily go through that membrane before. Now we have an actual structure. The fats aren't bonded together. They just all kind of come together like this. It's almost like another fat kind of squeeze in between them. So the more of that we have fat or lipid solubility, and the more we have of OHs, but not just OHs, other things on the periodic table. So if my wife comes in, he's walking around. Whiskey River. Oxygen, sulfur, nitrogen, phosphate. The more OHs, as well, will behave the same way. OHs, NH, pH, not pH like pH. Phosphorus, nitrogen, sulfur, hydrogen. The more of those, it's likely to be water soluble. It'll work fine with good old H2O. They're very similar. That's the difference between a polar covalent bond, the water example, or those others, versus the non-polar. And so when we look at a molecule, larger molecules, we look at its composition chemically, and we can determine whether or not, for instance, alcohol has a fair amount of water solubility, not entirely so, but it can. It's more water soluble. Glucose, even though it has some degrees that maybe, but it's more or less, it has enough OHs that it's water soluble. So here's examples of other ways they bond. Here's the double bond example. They don't draw the electrons the way I was taught, but it's okay. So here you have, again, equal distribution, and now the shape plays a role. Okay, oxygen is elegant. Okay, and it can attach to the heme of the hemoglobin, carry the oxygen to the tissues so we can live. I drew above there, that's COO, that's carbon monoxide, one oxygen. that is even better attaching to hemoglobin. That's bad news. Because that's why it's a toxin. That's auto exhaust rather, smoking, environmental toxins, carbon monoxide, everywhere. That's unfortunately how people try to kill themselves sometimes. Now you get in the garage, turn the car on, keep the door closed, open the window, it's colorless, it's odorless, it's terrible. Okay? Because once it adheres to that hemoglobin, it's almost impossible to separate. We see a lot of it in firefighters, and that's why they have what they are. There's a very good older movie called Backdraft that showed how they use hyperbaric or high pressure oxygen to try to treat that. We go into that in respiratory, circulation, and things like that. And yet there's another one, nitrogen, another gas. Nitrogen in us is relatively inert, but causes problems, particularly in divers, because it gets pushed in, and then when it comes out of solution, it creates bubbles. You get to that in respiratory and in pulmonary when we look at that in AP2, and it causes something called the bends that you might have heard in divers, where they have to do decompression stops. There's a lot, there's a tremendous amount of, it's biological science that plays, and that's a physical property, not a chemical. Because again, they're not really reactive. Oxygen is a little bit different because of the role it plays. So nonpolar equal sharing, carbon dioxide, a very good similar. And you see how it differs in shape from water? That's why people were taught for years. I was taught this. Oh, when you're breathing, the oxygen comes in and the carbon dioxide goes out. It's like they're on a bus and somebody got up and you took their seat. Carbon dioxide, no. Okay, carbon dioxide didn't take its seat. Oxygen came off. Carbon dioxide rides not on the heme, but on the globin. They're not the same. Or it dissolves in the solution. And when it dissolves in the solution, we're going to learn about it probably on Monday, if not on Wednesday. It forms something called a buffer. That protects our bodies from changes in pH. Very significant. The most important buffer in your body, which I go into ad nauseum. So polar, again, attracting ability overwhelms because of the shape. Because we're still dealing with hydrogens. And we get that electronegative, and they call it a dipole. So here it is, same, better than I could draw it. That's actually measurable. It's not 90 degrees anymore, but since these are both a little bit positive, they repel. Okay? It's like 106 degrees, not 90 degrees as you would think if they were equally spaced at any one time. You can measure that. And that accounts, and what this accounts for is a lot of what goes on in water. And we're getting to the most important one. Thankfully, I have 10 minutes left. It's like a race. I know there's a lot to present, but you have so much. So I wish we had more time to do this. Be more thorough. Reach out when you want to. If you have any, I respond to emails very, very quick. I have nothing else to do. Walk the dog. I'm fine. So here, it's not a complete, the transfer, ignore that. But it's just a magnetic attraction. Here, you have unequal sharing. Here, you have equal sharing. Fine, I'll buy that. Water is unique because of that unequal sharing. Okay, the hydrogen bond is the weakest of all the bonds, but it creates all these miraculous properties of water. Why? Because you look at this. It's an intramolecular bond holding the molecule in a three-dimensional shape. I don't do this one. Here. You'll see down the road when we get to DNA. If you're familiar with DNA, really the miraculous molecule of our body, it has the uncanny ability to, it's like a biological zipper. It can open and close. Hydrogen bonds. All because of its compositions with OHs and NHs and SHs and pHs. That's why there's a reason I do all this stuff. Okay. These guys, you see, they have a magnetic attraction, just like I don't want to walk through the cat. Make you a water, make you a hydrogen, you an oxygen, but you get the idea. It's a loose attraction. So do not do this at home, but appreciate the example. Take identical saucepans on identical burners, fill one halfway up with water, same volume, quart of water, it'll say a 4-quart saucepan, a quart of oil. Do not use the good EVOO, it'll break down. You can get the cheap canola or the vegetable oil. They're all whatever. Turn up the heat, put index finger in each. Which one are you going to remove first? Which one's going to heat up faster, the water or the oil? There's no such thing as a wrong guess. We learn. Which is going to heat up faster, the water or the oil? How hot can water get? One temperature, 212 degrees Fahrenheit, 100 degrees Celsius, boiling. How hot can the oil get? PDH, pretty darn hot. Okay, we call it the smoke point. We use avocado oil. I'm sorry, 500 degree Fahrenheit smoke point. The oil is going to heat up faster because the oil is molecules like this. They just cuddle together. As soon as you start to heat them, they start moving around. In order to heat the water, you gotta break these first. They may be weak, but they're abundant. Remember how many freaking molecules you got? And that's why water heats up more slowly, and it has a limit. Oil does not. And because of that, our body is very free. That's homeostasis. When it's hot outside, it's getting warm in the room. I got all this stuff on. Okay? Slowly. If you're not Steeler fans, you're in trouble. Lie and become one if you're here. I know, I can tolerate. Have you had to deal with Ravens? Here. Baltimore's a great city, great food city. Don't make crab cakes. Nevertheless, what happens is it accounts for those physical properties. These bonds are reluctant to break so they can absorb heat before your body doesn't start to boil. And when you freeze, they absorb heat. Moreover, when water gets cold, what happens when it makes ice? Okay, ice floats because these bonds are shortened. They get all the bonds become longer, so the molecule becomes less dense, even though it's solid, so it floats on the top. That's what happens in the Allegheny and the Yaak and the Mon and the Ohio River. When you get ice around here, they freeze over. And that has caused a lot of problems with flooding over the years. It still does. It depends on how hard a winter we have. It's caused flooding in a lot of different cities. So all of that plays a role. That's part of hydrogen bonds. That's called the water strike. I mean, there's not enough. It's the way the weight is distributed so evenly, it can't break down the attraction. We call that surface tension. That plays a really important role in expanding your lungs. It's not when you expand your chest, there's a little bit of moisture that the wall of your chest and the outer coating of your lung, it helps to pull. So it's really important. We need that fluid in there. Moisture plays a significant role. There's physiological reasons for all of this that are there. And at the very end, this is the part let me frame it this way. If someone in another course says to you, these are the reactants and these are the products, like this. These are the reactants, this is the product. Okay. For that course, answer the way they want you to answer. Living systems, reactions go both ways. They are reversible. When something is irreversible, it is bad. That denaturing the protein, you can't uncook the egg. You can't make the steak raw again. You just can't. So that's an irreversible in medicine and science is a bad thing, particularly in medicine. When you say, can this get better? I'm sorry, this is irreversible. That's not good news for a patient. We have things that are treatable, but we don't necessarily have things that are curable. Treatable is a good thing. Sometimes you're lucky and things go away. Doesn't mean they won't come back. So this is anabolic. We're making a bond to store energy. These are reactants and products. Yeah, but we can break that down like this. So here we can make it or we can reverse it in the other direction. It's not always goes that way equally. It's not as fast in one direction as the other. There's a lot of variation that's there. So anabolic, you make bonds, you store energy. Catabolic, they had a better example. You break bonds like this. So that's glycogen, the way you store sugars, very limited in your body. The liver or skeletal muscle, it's like emergency storage in case you have to run or fight. It's called the fight or flight response we get to at the end of the course. And it releases glucose as an available energy source. That's there. And then we have these exchange or displacement. Yeah, we do this all the time. But intelligently enough, they're not reactants and products. You're going to see, I was telling you about the carbon dioxide in the water. It mixes with water, and it creates a very interesting reversible reaction. that we'll talk about when we talk about buffers. And they're reversible, not everywhere, because it requires an enzyme to make it reversible. So it's a lot, and that plays a big role in respiration. That's why carbon dioxide levels are more about what make you breathe more than oxygen. So it's interesting stuff. And then this last molecule we'll get to later because I'm at the end. To me, it's as important as any molecule in the body. We get to this. It's called a nucleotide. Again, whatever you weigh, you make every day, you either make or break down an equal amount. You add up all those tiny molecules, and if you added them all up and calculated their weight, that's what you do. It's our energy currency. When we have to spend it, we break it down. When we're not using it, we store it back up. So we're constantly making it and then hopefully using it and storing it. If we do it equally to a certain extent, since we have to store it as fat, we do, it's like that 2,000 calories a day, which are heat units. And you want to ingest it, but you have to do enough activity to use it up. It's the old calorie count thing, which is a very reliable dieting thing, I might mention. And I think that don't do these. I promise you. If somebody asks you, the only way to remember it is this. I hate redox. I was a chem major. Oxidation means you lose electrons. Reduction means you gain them. It's a just because rule. Theoretically, is when you gain electrons, you're reducing the charge. Even a chem major, we hate redox reactions. Nobody likes them. Farewell. Have a great weekend. Good talking to you. Remember these guys at 1 o'clock.